Old computers are really super cool, and I definitely agree, which is why I decided to make an emulator for one from scratch in my beloved game engine, Godot. Before I start, this is actually really fun to make, and you should definitely try to make one for yourself. My emulator was for a chip-8 CPU. I'm not actually sure if it's a CPU or a programming language. It's kind of unclear. But since CPU sounds cooler and it lets me use the word emulator in my title, let's go with that. So a chip-8 can be broken down into its main parts: the timers, the input, its memory, and the display. The simplest for now is, of course, the display. The display for the chip-8 is a monochrome 64 pixel wide by 32 pixel tall screen. Display information is stored inside of a buffer within the machine. If you're confused, think of the buffer as like a really big array, around 64 times 32 big array. Inside the buffer, a pixel has a binary value, 1 for on, 0 for off, of course. Next, I guess we can look at let's go with the input. Yeah, the chip-8 is a little beta male computer that only has 16 possible keys that can be pressed, and guess what? The key data is also stored inside of a buffer, but it's only 16 places wide instead of the 64 times 32 big ass number. The reason there are only 16 possible keys is because of how the chip-8 designed its opcodes for input, and to get to that I have to circle back later after discussing memory, because there are a couple things you have to know about the memory before I can finish talking about the input. The chip-8 has 4 kilobytes of RAM and no ROM. Yeah, there's no ROM, and ROM is read-only memory. Everything, including the program, is stored inside the RAM of the computer, random access memory. This means that the computer can and does alter the program as it runs. To quote directly from the CogWAD's chip-8 technical reference, which was a massive help in this project, link in the description, the chip-8 language is capable of accessing up to 4 kilobytes of RAM from location hex 000 to hex FFF. The first 512 bytes from hex 000 to hex 1FF are where the original interpreter was located and should not be used by programs. Most chip-8 programs start at location at hex 200, but some begin at hex 600. Programs beginning at hex 600 are intended for the ETI 660 computer. Now, let's not break that down and just take the part that we need, pick and choose. Hex 200 to hex FFF is where our programs are stored in memory. That's not going to be important later. I just thought you should know that little tidbit because it is pretty interesting. Chip-8 has 16 registers. If you're a programmer, a register is just a variable that the CPU does basic things with, basically, usually math, other stuff. When the opcodes use a register, they refer to it as VX or VY. From now on, if you hear me say V, whatever, I'm referring to a register. The chip-8 refers to its registers in hexadecimal. For example, V1 is the first register, VF is the last register. When we're talking about VF, you should know it is known as the flag register, which all you need to know about the flag register is that it isn't used for normal stuff, because why the hell would it be used for normal stuff? Now back to the keyboard. Whenever we're looking at whatever key to check, the CPU looks at the first 4 bits of V whatever, it's defined by the programmer, which really limits how many keys you can have to 16 to be precise, because 4 bits is 16. I'm not going to go into how binary counts. You should have a little bit of knowledge. Now that we have gone over all the time, now that we can go over the timers, there are 2 timers, a delay timer and a sound timer. DT is where the delay timer is stored. It's a register separate from the 16 cool ass registers, except for VS. You can go Google yourself. The delay register is active when DT is not 0. The delay timer does nothing other than subtract 1 from the value of the delay timer at a rate of 60 times per second when it's active. When the delay timer reaches 0, it stops subtracting 0 so that it doesn't flip over and bit overflow, ST is, well, figure it out, Sherlock. I'm not going to tell you. When ST isn't active, aka sound timer isn't active, so 0, the computer will just constantly output a buzzing sound, and it also does the -1 thing that the delay timer does. The chip-8 only has 1 buzz sound, so there's no music, so it'll just, whenever the sound timer isn't 0, it'll just buzz, buzz, the same buzzing sound. It doesn't get old, trust me. Now we can talk about the opcodes. This isn't a tutorial, so I'm just going to give some base level info about the opcodes. There's 36 opcodes. Each opcode is 2 bytes long. My least favorite opcode is the draw opcode because it was a pain in my ass to get it working with no bugs. And if I had to say my most favorite, it'd probably be jump because it was fun and easy to implement. Now that I'm done with all the nerd shit, let's see this bad boy in action. Thanks for watching, bye.